How do you make steel? Today on the Roundhouse, we are answering that question, seeing how railroads play a role in creating it, and how you can model the process. All aboard!
In days past, the roundhouse was where the railroad worker united with the steam locomotive, each to prepare for the journey ahead. Today, it's where we examine the history, the industry, the machines, the hobby, and the passion behind railroading. News, interviews, stories, and more. So climb aboard. This is The Roundhouse.
Welcome to The Roundhouse. I'm your host, Nick Ozrak, and this is episode number 65 of our Trains and Railroading podcast, where we're talking about everything in the industry and the hobby. You name it, and we discuss it. And today we're talking to Bernard Kempinski. He is the author of The Model Railroader's Guide to Steel Mills. He is going to talk about how steel is made, how railroads play a role in it, and how you can model it. If you have a big space, if you have a small space, this is a listener request, actually, from Donald Dunn, who wanted to learn more about steel mills and how to model them. So, Donald, here's your episode, and this is a really interesting topic, so I'm glad we have a chance to cover it. Before we get to that, though, I want to take an opportunity to thank all of you who've made our Patreon campaign successful so far within the past few months, and I want to just go ahead and name all of the supporters who are currently contributing at least $1 a month to the show, and that includes CJ Griggs, Dan Smoley, Dwayne Furing, Etienne Ozrak, Jonathan Auclair, G4, Bruce Harrison, Chris Hoffman, Robert Carlson, Stuart Sterling, Elizabeth Ozrak, and Jim Lipnitz. You guys are awesome. Thank you so much for helping to support the show. And because of that, we are able to do some pretty cool things down the road. If you've been enjoying this summer's episodes, like the Joliet Rocket or the World War II train, believe me, there's more where that came from. And even if you can't subscribe to Patreon on a monthly basis, even if you could just make a one-time donation, every little bit helps us out and allows us to do some pretty cool episodes. So I wanted to give an opportunity for you guys who are already on Patreon supporting the show to be recognized. And if you haven't already, just subscribe for $1 a month and you'll get a shout out on a future episode just like this. Our guest today is a published author and renowned expert on steel mills, the railroads that service them, and how you can model them. Please welcome to the Roundhouse, Mr. Bernard Kempinski.
Good evening.
What began your interest in steel mills and the whole process of making steel?
Well, I'm not a steel professional. I'm a mechanical engineer, and I've worked most of my professional life as a defense analyst, working on weapon systems and such. But I was interested in steel as a rail fan many, many years ago, and took some pictures of steel mills with trains. It is a fascinating process when you go by a steel mill at night, especially like an electric arc furnace at night. You get real close and hear them making the noise and stuff. So around 1996, I got a request from the Walters Corporation to help them make a model of a steel mill. They had introduced an HO model, and they wanted me to convert it to N scale. And so that sort of started the modeling process of it. And then I started doing some more research, really started digging into it. And then later that became a book with Combat Publishing on steel mill modeling. Over the years, I built 2 model steel mills. I got rid of both of them. I may go back when I retire and do like a 1920 steel mill. So that's how I got started.
Let's start with a very seemingly basic question, but a lot to it. What is steel?
I cover some of this in the intro of the book, but basically the Iron Age started almost 4,000 years ago. So people knew about iron. But steel, and this is hard to believe, but until 1860s, steel was a relatively rare substance because it had to be handmade in a puddling process or a cementation process or some other hand process involved a lot of labor. So now we are so used to steel, it's hard to imagine that prior to, say, 1860s and the Civil War, steel was reserved for only critical applications like weapons and tools. So you couldn't just go buy steel. So even railroads did not use steel in their rail, for example. They used wrought iron. So steel is an alloy of iron and some other compounds. Carbon, chromium would make it stainless steel, manganese, and if you have phosphorus in it, that makes the steel actually more brittle. Iron is just a raw element. It does not exist in nature in raw iron. It always comes in oxides, except if you go way back billions of years when there was no oxygen, then you did have elemental iron just floating around. But in current days, we have just iron oxide. So that gets mined, and it goes to a steel mill where it gets converted, or to a blast furnace where it gets converted to pig iron. So that separates the oxygen from the iron. And we can go into the chemistry of that if you want, but it's a little bit dull. Basically, the carbon, you mix carbon with steel, you heat it up, and the carbon absorbs the oxygen, and the iron comes out. And then from the blast furnace, it would then go as pig iron to a converter. And that technology changed quite a bit in the last 150 years. And that's where it gets made, the iron gets made into steel. What you do is you add carbon to it. And one of the things I wanted to cover in the book is, why does adding an element like carbon, which is a soft element, to iron make the iron stronger? And the answer is pretty complicated, but to sum it up, it's basically the way the carbon interacts with the iron crystals. And it basically gets stuck in between the crystals and makes the crystals harder to dislodge. And so that whole process is what makes steel, by adding carbon. It's only like 1% to 2% carbon makes iron into steel. And if you get up around 4% carbon, then you have cast iron, which then starts to lose its toughness and becomes brittle. But cast iron is useful in other applications like engine blocks and parts that wear. So that's basically what steel is. It's an alloy of iron and some other elements, but particularly carbon.
What is the history of railroads' connection to steel manufacturing?
They kind of happened in parallel. Actually, railroads, mainstream railroads, started a little before steel was readily available. So the early railroads started in the United States in the 1830s, and commercial production steel didn't really start till the Bessemer process, which was 1866 in the United States. So I started a little earlier in England because the Bessemer process was invented in England. So what you had was the original railroads were iron. They were based on iron. That's why they call them the Iron Horse. And when steel came along, it became a self-feeding frenzy, but the steel made you able to have bigger engines and stronger rail, which then meant you needed more steel. So the steel mills got bigger, which led, a vicious cycle until you got to where we are now, where engines are quite big and powerful. So the railroads and steel are intertwined, and they were even integrated. Carnegie was a steel guy, but he started off with the U.S. military railroad in the Civil War, and then he became a railroad executive with Pennsy, and then he became a steel magnate. And he had his own steel railroads. So they are intertwined. And one of the cool things about modeling steel mills is that there's probably no other industry that relies on railroads to move the steel in the plant as much as a steel mill does, or move the raw materials and the iron and all that. Paper mills do to a certain extent, but steel mills, from one process to another, frequently rail cars are used, although now they're switching to wheeled vehicles in the future. So they're very much intermixed, and it's a match made in heaven.
Because there are so many railroads that have connection to the steel industry, as you were doing your research, what were some of the notable railroads, either as suppliers of the raw resources or as plant railroads?
You could say all of them, but the notable ones would be probably, the Union Railroad in Pennsylvania, in the Pittsburgh area, was sort of a amalgamation of a bunch of different railroads that worked in that region. The EJ&E in Chicago is another famous iron ore railroad or steel mill hauling railroad. Some of those railroads, like the EJ&E, branched out into other commodities. So when steel kind of went down in the U.S., the production of steel, they still had other business. Whereas other ones, like the PB&E that belonged to the Bethlehem Steel Railroad, didn't do quite as well when the Bethlehem Steel went away. But there's the Bestman. Lake Erie was a really great one. That was Andrew Carnegie's railroad that I mentioned earlier, and it went from the lakes. It wanted to bring iron ore from the lakes to Pittsburgh, and then it would backhaul coal to so that way they had loads going each direction. The Delray Connecting Railroad near Detroit was a good one. I mentioned the EJ&E, the PB&E, and then even the Pennsy and C&O, Norfolk Southern, they all supported steel mills. Actually, not in this book, but in my latest book on waterfront terminals, there's a map from the 1920s that shows where all the steel mills were in the 20s. And there were a lot in the 20s. There were probably like 40 or 50 in the United States. Right now, we're down to about 10 blast furnaces. We still make a lot of steel, but it's made in electric arc furnaces with recycled steel mostly. But you still need to take iron ore and convert it into steel for the high quality applications. And believe it or not, one of the most demanding applications is the highly drawn auto bodies, the stampings that they make for fenders and hoods and such. They require very high quality steel so that when they do the stamping, the part has no flaws. And the problem with recycled steel is you never know exactly what the composition of the scrap that you're putting in there is. And so when they melt it, then they do a little test. If it has too much of the wrong materials, particularly if it's an alloy like chromium or manganese, the only way to get it to the right specs is to add more pure iron and mix it up that way. So that's why the blast furnaces have not gone completely away in the United States, but we've lost a lot of that business to overseas steel manufacturers.
Let's take a visit to a steel plant. Could be a real one, could be just sort of general template. We got our hard hats on.
Steel-toed boots.
Steel-toed boots, very important.
And goggles.
And we've got all our proper PPE on, and we're going to take a plant tour, and we're going to observe the railroads and the flow of these raw materials. So why don't you guide us through the process? We've got our ore, we've got our coal. What are we going to do with it?
Okay, well, first thing we should say is that let's go look at what they call an integrated mill, because that's where the whole process is done. There are mills that just do one step of the process, like they call them merchant facilities. So you could have a merchant blast furnace that just makes pig iron, and you could have a merchant foundry that just makes parts and so on. But let's go to a big one. A lot of them are gone, but the one that I personally toured was Sparrows Point. So we can talk about Sparrows Point. So when I visited Sparrows Point in the 90s, it had one massive blast furnace. It was called Blast Furnace L, and it could do, I forget how many tons a day. Those numbers are in my book. I could look it up. But it was big. It was as high, it was like twice the size of the other blast furnaces around the United States. What happens is iron ore, coal, and limestone come in, usually by rail car, although at Sparrows Point, they also get ocean-going ships that could come in. By the way, Sparrows Point is closed down now. It was in Maryland near Baltimore. And so those three commodities would come in, and they would be stored near the blast furnace. And when they were needed, the blast furnace, in this case was done by conveyor, would bring the commodities up to the top of the mill, up to the furnace where it would be dropped into the blast furnace. And the blast furnace is an interesting process. It's not a uniform mixture inside there. So at the top, the things are relatively cool and they're new, but at the bottom, the things are really hot, and you have melted material way at the bottom. You have this central piece, which is called the dead band, which is glowing because it's incandescent. It's very hot and it's combusting. The carbon around it is combusting. And then as you go higher up in the blast furnace, you have layers of iron ore, coal, and limestone iron ore, and those are all starting to react and get hot and melt. Periodically, there'll be enough molten material in the bottom that you have to drain the furnace. And so the way they'll do that is they actually use an explosive charge, and it's like a shape charge, like an anti-tank weapon, and they will blow a hole through a port and drain the iron ore into a trough, and then it'll be distributed to various loading spouts where it can go into what they call a hot metal car. They also have a thing called a slag notch or a monkey, and sometimes they will drain the slag off separately. That's called flushing the monkey, which I always thought was a cute expression. And that's done similarly, except that they let the slag plug up that hole. They don't necessarily pack it. When they're done draining the melted material from the blast furnace, they seal the hole with a gun that shoots clay in, and the clay hits the hot material and basically bakes into like a ceramic plug. And then the whole process starts again. And in fact, once they start a blast furnace, they call it a campaign, and it will go up to 10 years without stopping. It's a continuous process. So now you've got hot metal in the bottle car, and you take it to the next step in the process, which would be the converter, which would be either, nowadays it's usually a basic oxygen furnace, but prior to this, it was in an open hearth furnace, or even before that, it was a Bessemer furnace, or way back before they had the Bessemer furnace, it would go to a puddling furnace. And in those places, that's where you convert the pure pig iron into steel of the various concentrations. It's a pretty cool process. The basic oxygen furnace, to be economical, they have to be quite big, so it's usually like 300 tons at a time in the vessel. And the way it works is they have a thing called an oxygen lance, which comes down into the vessel and it shoots oxygen into the ore, and that helps burn off the impurities. You also have I mentioned the limestone. The role of the limestone is to absorb the impurities, and that's what forms a slag, which you strip off. And the Bessemer furnace process is similar to the basic oxygen process, but the Bessemer, when they had that process in the 1860s, they did not have a way to economically make pure oxygen, so they just used regular air. But if you remember high school chemistry, regular air is mostly nitrogen, and that's not good for making steel. So Bessemer steel had a problem in that it was hard to control the quality because of the large hydrogen content. So once they got commercial tonnage quantities of oxygen, the basic oxygen furnace was superior. But in between, the open hearth furnace technology filled in that gap. And open hearth was developed about the same time as the Bessemer furnace, but the problem was they couldn't find materials to make the furnace that were able to withstand the extremely high heat the open hearth furnace would subject the furnace to. So you got to remember, steel melts around 3,000 degrees. So anything around it is going to melt except for the ceramic type materials and fire bricks. So you pretty much have to build whatever you're building, line it with these fire bricks, and then have the steel structure. You can't let the steel itself touch or it will melt. So it's pretty impressive to watch. When I was at Sparrows Point, I watched them pour a hot bucket of cast pig iron into the basic oxygen furnace, and it was pretty cool because we were in a pickup truck down at the ground level, and this was happening probably 100 feet over our head, and sparks are flying everywhere, and it was pretty cool. And another thing to realize too in a steel mill, which is kind of scary, is that it is a liquid, and so if they spill it, it runs just like a liquid until it cools off, and there's no stopping it. You can't throw a paper towel or absorb it. So there have been some horrific accidents in that regard. But okay, so now you've got the steel being made in the converter, and in the Sparrows Point, it was a basic oxygen furnace. Then it would go to what nowadays they use a continuous caster. In the old days, they use ingots, and you would pour the ingots. They're like little square rectangles, and then those would go to rolling mills. But now they just go straight into a continuous caster. It's a more efficient process because you don't have to reheat, and that gets rolled into the shapes eventually that you want. So all that happened at Sparrows Point. It was an integrated mill. It went from raw materials to finished shapes. Another cool one to talk about would be the Rugge steel. Rugge? It's River Rouge, I think is how they say it now. It's not like Rugge one in the movie, out in Detroit. And there they go from iron ore and rubber and glass to cars, which is pretty cool. That's a fully integrated factory. It was developed by Henry Ford. I don't know if that answered your question about the basic process, but that's what happens in a steel mill.
Oh, that definitely answers it. As we're looking around this plant, or a general template, The thing you notice is that the freight cars that these steel mills use are not like what you'll see out on the main line. What are some of the primary examples of steel mill specific freight cars?
Well, the first one I just mentioned is the bottle car, or sometimes called the submarine car. And it's the car that's designed to take the hot molten cast iron out of the blast furnace to the converters. And it looks like a bottle on its side. It has a spout. It rotates. They can be very large. It can be up to 300 tons. So they have multiple trucks. There are some that have 16 wheels or more. And it's lined with fire brick. You will occasionally see those on mainline runs, though, because if there's a steel mill that needs, maybe their furnace is down, but they want to keep producing steel, they will get their hot metal from another plant. It could be 100 miles away. You have I forget the exact number of hours, but you have 2 or 3 days before the iron starts to solidify in the bottle car. And if it's getting to the point where the iron is getting cool, they can actually stick a lance in it and keep heating it up to avoid that. Because if it ever cools in the car is ruined and has to go back and be scrapped. They were telling me at the Sparrows Point visit one time that because these cars are so heavy, that one of them derailed right in the basic oxygen furnace plant. And they had 2 days to get it out. They had to bring in a special crane that could pick it up. And that crane had to come from someplace like Ohio or something like that. So they were really sweating whether that would happen or not. So the bottle car is probably the most unique one, and there are models of those available in HO and N and maybe even O scale. The next one is sort of a ladle car, which is another form of hauling hot metal around, and it just looks like a cup, a ladle with a little spout, and it'll be used in in-plant movements. You probably wouldn't see that one on the open road. And then there's the slag car, which looks like a thimble. And it's designed to take the slag from the converters, not usually from the blast furnace. Well, there's some in the blast furnace too. A lot of blast furnaces will just let the slag go into a pit, let it cool, and then break it up. But others will take the slag and the thimbles from the blast furnace to a separate location where the slag is. By the way, the slag is not wasted. It is recycled. It has many applications. One I found very interesting was it's ground up and used as a sandblast material for blasting paint off of rusty metal. So that's also used, it's not wasted. It can be used in road construction and a bunch of other things. So the slag car looks like a thimble. Models of those are available. There's a whole assortment of flat cars that they use on the mills. They're called mill gons because they have to move the slabs around on the mill. So you have a variety of those. You have the coil cars that move the materials when they're done. Those are kind of cool. And then any kind of flat car or bulkhead flat car could be used to move slabs. If you ever rail fanning, you see a bulkhead flat go by and it only has 4 or 5 plates on it. That's because those plates are really heavy and they can only put that many on a bulkhead flat. You have lots of hopper cars because various materials are coming in and loose. The iron ore hoppers tend to be smaller, shorter, little shorty cars because their iron ore is more dense than coal, so you have to have a small car. But you also have the bigger regular hoppers to carry coal and to carry limestone. And usually when you site a steel mill, like when they're originally setting them up, you try to pick it so that it's near one of those 3 commodities. It could be near the iron source, or in the United States, we tended to have them mostly by the coal sources and bring the iron ore down because the iron ore, well, at first iron ore was all sort of over the Northeast, but those were smaller pockets and they got used up pretty quickly. There was, for example, one in Virginia out in Lowmore that had iron ore deposits that were nearby, but by the 1920s, that was finished. In New Jersey, they had these things called bog ore, which was iron ore that was in a swampy area, and that got used up pretty quickly. The pattern that developed, say, by the 1920s was the steel mills were near the coke or the limestone source, and the iron ore was coming down from Minnesota, a couple other locations. Alabama had a few. There were a few out west. And so that's the type of transport you would see. Another thing not forget is that water was used a lot to transfer these materials. Iron ore came by ship and coal and vice versa. So you frequently will have blast furnaces on rivers or on the Great Lakes so that they could exploit the water transportation. I guess that's it. If I think of others, I'll let you know.
When I think of steel mills, I typically think of the bottle cars and I knew them as slag cars, but essentially, yeah, the teacups on wheels in a way.
Those are slag cars. Stay away from those, by the way, because they can explode. And how does a slag car explode? It's basically if they get moisture inside them. If there's like a load of rock that has water in it, and that water hits the slag, it can cause immediately create steam, which then causes the thing to pop. And I read several accident reports where people walking by, like at Weirton Steel, there was a case where a man was walking home. He was a steel worker, and he's walking home for lunch, and he got killed by an exploding slag car that went by. So be careful. Oh, Coke cars. I forgot to mention, this is a cool one if you're a rail fan. You'll see the Coke Express cars, and they're like high cube hopper cars because Coke is very low density, so you can put a lot in one car. So those are cool. Did I mention the ingot cars? On a steel mill, you would have flat cars with little ingots. That's another cool type of car that you might see on a steel mill.
Switching our attention to the locomotive roster, obviously coal and ore is coming in via the main lines and via whatever power they're using. But as you researched for your book and looked at steel mills across the country, what were some of the trends as far as initially steam locomotives and later diesels?
Yeah. They're typically smaller engines, even narrow gauge. You have steel mills with narrow gauge railroads on them. Bethlehem Steel had standard gauge and it had a small narrow gauge railroad. They even had a couple specialized wide gauge cars to move the coke and things around. But for motive power, typically it was small switching engines like SW1200s or MP15s. I've seen some larger engines like GP7s and GP15s. On steel mills, older engines that came off the main line, typically, nothing too outrageous. I can't think of too many mills that custom made their cars, although there probably were some of those. They also had like funky critter type things that would do just specialized moves. They might have a little critter that moved the coke car from the coke wharf to the cooling shed, and then just do a little shuttle back and forth. So you would see something like that. Also on the High Line, which is where the raw materials are brought in, and then they called it the High Line because it would drop the materials down the bottom into piles. You could sometimes see specialized cars doing that. But you could also use an SW1200 or something just to do those kind of moves. They had their own paint jobs, which is kind of cool. So you could see a lot of different paint jobs on the steel mill railroads. And there have been several books published on that, covering the various schemes that they use and the type of locomotives. Sky's the limit there, really. You wouldn't probably see -9s or -8s in steel mills, though, not yet. Maybe in the future we might.
We have a listener submitted question from Richard Boye. Hope I pronounced your name right. Subjective question: why were blast furnaces always named for women?
Well, they weren't always, because some of them just had numbers. But I guess it's kind of like a boat. It's just a feminine. You always say she's a great ship. We in English language don't maintain the gender difference in our articles, but other languages like French, and they say la and la and all. So I think it has to go with that the fact that it's a feminine thing, but I don't know the answer for real. I'm tap dancing around it.
Well, it's the kind of thing where often steam locomotives, it's the same thing. They're given women's names as well. So I think it's just because typically the employees were men, and because they had the working relationship, it just seemed like a natural progression of things.
Although in the Civil War, and I do model the Civil War in my home layout, one of the things I like about that railroad is the locomotives have names, not numbers. And so they're not named after women. I have Fury, Leach. They're actually named after a lot of the railroad executives. McCallum, Hopt, and Whitten. So those are all, 4 of those are named after people, men. And then one's just named Fury, but there was, I did a model of one called the Velocity, which I thought was a cool name. There's the Osceola, which is named after an Indian tribe. So yeah, it could be other things. The Jupiter, right, from the Transcontinental Railroad had a name, a non-woman's name.
For those of you who are listening to get ideas because you've seen photos of steel railroads and you're saying, I want to model one or I want to include one on my train layout, we're here for you. We're going to look a little bit at how you can make that happen. So Bernie, I guess a good place to start is how much space do you need to model a mill?
Well, the sky's the limit. I mean, you could just make a whole 10,000 square foot model railroad of a steel mill, but most people don't do that. So there's a couple alternatives to capture the feel of steel without actually modeling the facilities. A blast furnace is a pretty big object. And one of the problems with it is it's not necessarily a linear thing. It's almost as wide as it is long. And so that immediately in the larger scales creates access problems because they typically have tracks on both sides. If you're working in a smaller scale like N scale, I built my first steel mill. It was a full integrated steel mill in 3 by 10 feet. And I had one blast furnace. I had 4 open hearth furnaces. I had a rolling mill, and I had a full coke works where the coal is converted from coal to coke. I didn't talk about that process, but that is another intermediate process, or that's another raw material that steel needs, that you have to take coal and bake it in the absence of oxygen to get rid of the volatile material and just reduce it to elemental carbon. And that's what the coke is. And you can't let it get oxygen when it's baking because it'll catch on fire. Once you have the coke, you drop it in the blast furnace, and that's what reacts with the ferric oxide. And the carbon grabs the oxygen off of the iron and becomes CO2. And by the way, for the environmentalists in the listening, there is no way around creating CO2 when you make steel. That is the process. You take iron oxide and you make iron and carbon dioxide. So unless you recycle it, there's no way of getting around that. Cement, by the way, is similar. So I did a steel mill in 3 by 10. You could do a small merchant furnace in HO scale and probably a 2 by 4 with just maybe a few support tracks. So that's sort of the minimum size. But if you wanted to do like a full steel operation, you would get rid of the blast furnace and just do a mini mill, which is electric arc furnace. Then you would be getting scrap, maybe some pig iron, because I mentioned you have to dilute the mixture to get the strength that you want. Those kind of buildings look more like just regular sheds. And I've got one in my book that's about 10 by 12, and I think there's like a 4 by 6 mini mill in the book. So a mini mill would be an easy way to do it in HO. Model in N scale if you really want to do the whole thing in a small space. Or the other alternative is to go back and model the early mills from like the 1920s and the 1910s or maybe even the 1890s. They were much smaller facilities back then. There's a guy in the book who did one of those, and he did the Schuylkill Ironworks in HO scale in a 4 by 21 foot space, and he had a full integrated 1890s era. His name was Eric Craig. He did 1890s era or early 20th century with steam and brick buildings, and very cool. I mean, like I said, if I were to do it again, I would probably go back into that time period and do a really early one.
Because the technology has progressed well, the process has evolved, the technology has evolved with it. So you choose a particular era, you're not only looking at particular rolling stock or motive power, you're also looking at certain types of industrial architecture to go along with that.
Correct. Yeah. Well, the other advantage, though, is that everything was smaller back in that time period. You don't have 100-ton cars. You have 50-ton cars, and you have 260s or 080s working in the plant. The engines aren't so big. But to try to do Sparrows Point in HO scale in the modern one, the furnace would be about 4 feet tall. That'd be pretty big, and probably 5 or 6 feet square. So that'd be a big one. So the earlier you go, and I believe I have a table in my book that shows the relative size of these things over the years. And yeah, the 1940s is a good sweet spot because you have steam to diesel transition. You have relatively smaller furnaces. The facilities were big, but they had multiple blast furnaces. You would see like 6 or 7 blast furnaces in a row. So you could model, say, 2 of those. And, so the ancillary buildings, the rolling mills and the converters, in not that big a space. Still need quite a bit of room, though. There have been a few people that have taken the concept and just done a whole basement full of steel mills. And it's pretty cool. I like this kind of stuff, but people like my wife or visitors will come down and they'll like, why did you want to model this? To them, it's an eyesore. But to most model railroaders, we think it's cool. But anyway, so that's another factor you have to consider. You're modeling a dirty, gritty industry.
That and the fact that the steel industry is what makes and has made modern railroading possible. Steel rail.
Everything. Ships and, yeah. Well, it's kind of cool if you go back to like the 1870s. One of the interesting factors that affected the steel industry was the desire to make armor plate for battleships. And that really advanced the technology. The Navy back then was paying for a lot of the research by basically giving contracts to the steel producers to say, hey, I want a steel plate that can do this, keep out this size of a bullet with this thickness of steel. And the steel mills had to develop that stuff. They had, like in Bethlehem, Pennsylvania, had these huge cementation ovens where they would put these big slabs, these armor slabs, pack them with charcoal and let them sit there for a week. And in the cementation process, the pig iron would absorb the carbon. And so you had a material that had different varieties of carbon or different concentrations of carbon. It would be more carbon on the surface and less in the middle. And then this had to be processed by folding and bending and hammering and wrought. That's where the term wrought iron comes from. You had to process the material to get the even consistency that you wanted. One of my favorite stories about the wrought process is Japanese katana swords. You've probably heard about them, right? They have a reputation of being sort of the strongest, toughest sword ever made, and yet they started with some of the crappiest raw materials that you can imagine. It was called tamata, something like that, steel. But through the process of, they would heat it up, melt it, and then they would make this like spongy slab of iron, and then they would proceed to fold it over on itself. And after 14 folds, I think the numbers are right, you get like 16,000 layers. And those layers are where the strength came from. And then the sword itself was made with all different pieces, so it had a very hard bottom edge. It had a nice tempered middle piece. And I didn't mention heat treating, but the heat treating is another aspect of steel, although modelers don't have to worry about it too much because it just happens in the building. But anyway, so I got on a little sidetrack there about the whole process of making cool specialty steel, let's put it that way.
Well, that's the thing. You just recognize how vital it's been to industrial development and how ubiquitous it is. It's everywhere. It's part of everything, practically. And it's not until you step back and look at the whole process of it that you realize how much vital role that plays. I mean, certainly for us rail fans, where our favorite locomotives are made of it and running on it, it makes a particular difference. But even in our daily lives, we're driving over bridges made of it. So it makes sense that it has always been a very important and very large industry. Now, for folks who want to experience being able to see a mill, and obviously it's tricky because plants are concerned about security and stuff like that, but what are some ways and places that people can get the steel mill experience that you're aware of?
To see an active mill is very difficult. Typically, you'd have to work with a professional organization. The NMRA has a rail heavy industry SIG, at least they used to. I'm not sure if they still do. And they will occasionally get plant tours, and they require the safety gear. But if you are just on your own and you want to see a blast furnace up close, the best one to go to is in Alabama, in Birmingham, Alabama. It's the Sloss Furnaces. It's, I believe, a national park. And you can go there and you can practically crawl all over a steel mill. You can go down into the bottom of the skip hoist where the rail cars dump their loads. I went there it was like 95 degrees the day I was there, but when I was down in that tunnel, it was nice and cool. It was 50 degrees. There were some places where they let you crawl or walk upstairs, and you can actually touch the blast furnace and see they're really complex structures. I mean, if you were to model a blast furnace to the same level of detail that we model a locomotive, it would take months because there's pipes and valves and all kinds of stuff everywhere. It can be quite a challenging modeling project. The other thing you might be able to do is set up, there's mini mills all over the United States. There's probably 60 or 70 of them. Every state has a couple. And if you contact their public relations people, they sometimes have open houses where you can go see what's going on. There used to be a really cool one in Weirton, West Virginia, where you were on a public road, but it was an elevated road that went right through the middle of the plant. So you could stand on the sidewalk and just watch all kinds of cool stuff. Trains would go right underneath you, and you could see the bottle cars moving around and all that. Unfortunately, that mill is largely closed now. So, yeah, it's tough. It was even before 9/11. The mills were very, very security conscious because it's dangerous stuff that they're doing, and people don't know what they're doing could easily get hurt.
A lot of very hot stuff, basically.
Hot stuff and high places and stuff dropping and all kinds of ways to get hurt. The other thing about Sloss, by the way, is if you're curious and you're curious about whether you want to go or not, the Historical Architectural Engineering Record, which is a form of it's stored at the Library of Congress, has a lot of the stuff online. So you can just Google HAER, Library of Congress, and type in Sloss, SLOSS, and you'll see hundreds of pictures of this place and nice engineering drawings of what it looks like. And it'll give you a good feel. And then if you feel compelled to go actually visit, then you have to go to Birmingham, Alabama.
I'll have that link in the show notes too, so people can check that out. And of course, we'll have plenty of photos from Bernie illustrating a lot of what we've discussed about today. And a good place to end this is for getting more information and going even further into detail about steel mills. We have your book, The Model Railroader's Guide to Steel Mills. So provide us a general overview of what you've included in that book.
Okay, well, it's a standard Comback Publishing modeling handbook, so they're about 95 pages. And when I did the book, I wanted to make it such that it would be of interest to people who weren't even modeling steel, but they were just curious about the process. And so I talk about some of the stuff we just talked about. So it starts off with the history of steel, the iron making process, the steel making process, and railroads and transportation. And then that's the first 45 pages. And then it gets into track planning and then putting it all together with a big case study on, I use Sparrows Point. And then the last 20 pages are modeling techniques on how to build the various structures, how to weather the freight cars and that kind of thing. So it's a little bit of everything. I wanted to have even more in the book, but with the 90-page format, we had to cut out some stuff. So they left out the chemistry, so don't be worried. I wanted to put the chemistry in, but we didn't put that in the book. This book, by the way, it's been out for a couple of years. It got published in, let's see, what year did it get published in? Around 97, I think it was. Let's see, was it? No, it was 2010 that it got published. But it still sells very well, and on Amazon it gets very good ratings, so I can't complain.
Very good. Well, we'll have a link where you can check out his book as well. And Bernie, thank you so much for joining us here on the Roundhouse to walk us through a process which we take its final product for granted a lot, but it's really interesting to break down the elements of it and see what goes into it. And boy, if I could fit another layout into my apartment, you better believe you make a good case for it being a steel mill. Bernie, thank you so much.
You're welcome.
And now, the question of the day.
What is an event that you've been to at a railroad museum or tourist railroad that drew you there besides the normal operation of trains? Couple of responses to share with you. First, from Kenny Broomfield. For me, it would be the Reading or Pennsylvania days at the Railroad Museum of PA. And Wayne Wanzer and Keith Maiden Jr. responded that they've both been to train robberies. That's an interesting one. I haven't been to a train robbery myself, but there is something perhaps behind a steam locomotive that would be special about seeing guys ride up on horseback. And some places I know the way they do it is that the money they rob goes to a particular charity. So I think that's a pretty cool way of doing things. Your question of the day for this episode is, what type of industry serviced by railroads is your favorite? Let me know on the roundhousepodcast.com, or you can join the conversation on social media. We're on Facebook and Twitter. Thank you guys, as always, for your support. And remember, as always, that the Roundhouse is our house.